Okay, so let's continue where we are. I wanted to work a couple more of these things just to show you again that we had mentioned. What would that be? Since this is the base, I want to represent e to the fifth as the power of the base. Since they match, that exponent is what we're looking for. Okay. How about if I do this? Anytime this matches, it's that exponent. What is that understood exponent? That's just 1, because e to the 1 is equal to e. Okay. So there's not a lot of these I can't use properties. So some of these strange through. Now here to me is one of the most important results, that I can represent any number, right? Any number. So, these are obvious, right? 8 is equal to 2 cubed. I want to represent 8 as a power of 2. What is it? 3. Those are kind of obvious, but here is it not so obvious that I can represent any number as a power to any base using the log, and this is the log base b of that number. That's what that power is. So for instance, I want to represent 43.0031 as a power of 10. This is crazy, like 10 to the 0 is 1, 10 to the 1th is 10, 10 squared is 100. This doesn't even lie between that, okay? I can't do this by hand. I can kind of do some guesses. They would be, maybe within 2 or 3 points or something, but it's not necessary so. But here, in order to find out this, I've got to use, what do you want me to raise that power to? 10. So if I go to my calculator and understood now, so I'm going to do the log. Let me clear this out. I'm going to use the log. That's the base 10. It's understood. So log, and now the 43.0031. If I do that, that's going to give me 1.633. Let's go 5. And let me see if this works. Does 10, so question mark, does 10 to the 1.6335 equal to 43.0031? And this is a big question mark. But now if I go 10, and then I use my power, let me go back here. So I do my caret key to get my exponent, and I'm just going to copy that down to get all of the decimal places. That gives me 43.00399, which rounds out to 31. The 0 goes to the 1. Okay. You say big deal. I say, well, let's try something else. Let's go 40. I want to represent 43.0031 as some power of, let's go E, since these two bases are readily available. Let's go some power of 2.718. What is that? It's a different number. I'm going to go here on my 30. I'll go LN, and then the very same thing, the 43.0031. And it tells me that is 3.76. So this would be the 3.7613. Okay. The LN of 43.0031 is equal to 3.7613, which says if I can represent 43.031, is this for real? E to the 3.7613. And now if I go and if I find my E, second E to the X gives me that, my E to the X. And if I copy that number, Let me see if I do it this way here. Let me see if I can get it here. No. I'm going to have to type in that number. Second, e to the x 3.7612722206 43.00. Let me let you see it. 43.00309999. This is the amazing results with log, is that I can represent any number. I can represent this as a power to any base that I want to. What is my x? It is just the log to that base of that number. I can represent this as a power of 3, as a power of 5, as a power of 7. And this is a really unique result that I can do it with just the log, the inverse log at that point. Okay. All right, so let me go through. These are all calculators. So let me kind of go back through and let me hit these on the calculator. You should be doing it at the same time. I'm going to bring out my 36. And I want to do log 200. So here I've got the log is understood 10, and that's it that you're using by yourself. So here's the ln log. This is the one that gives me different bases on here. So ln, I toggle it again, gives me the log 200. And that's just 2.301. So 10 to the 2.301 should be 200. Okay. Log 0.074. How about the ln of 200? So I'll hit the ln one time, the 200, and that gives me 5.298. Which says that if I raise e, that base, to the 5.298, I should get 200. So here's some basic properties as we go through. I want to do basic properties and then we'll kind of start working these things. Okay. We'll come back to some of the basic calculations. Any base, here's some properties, okay, basic properties of logs. That if I take 1, if I do the log of any base b, that's going to be 0 because it doesn't matter. I want to represent 1. This is kind of my mnemonic. I want to represent 1 as a power of b. The only way I'm going to do that is b to the 0. Any number raised to the 0 is going to be equal to 1. So the log to base b, any base of 1 is just equal to 0. What about if I want to do b? The log of b, if this thing is the very same thing as that. So let me do a couple of examples over here. The log 10 of 1, that's equal to 0. Log 21 is equal to 0. Log 3 of 1 is equal to 0. 3 to the 0 is equal to 1. 20 to the 0 is equal to 1. 10 to the 0 is equal to 1. Okay? And now if these are equal, the base and the number that I want to represent, now that's 1. Okay, because I want to represent b as a power of b. What is that? Exponent, that's just 1. Right? That's the only way this will work is if that's 1. So for instance, If I see log 10, I've got to recognize this case that this is 10, the base 10, that's just 1. What's the natural log of E? That's just 1 because that's the base E. With the natural log, that's the base. So this is the very same thing as log base E of E. But instead of using this notation, I use this notation. Okay? This would have been the very same thing as that. Okay? This just happened to be understood 10, so we drop that. Okay? If this is one that we saw a while ago. If I'm taking b to the x, if this is already represented as a power, this is the same thing as this. I'm already representing some number as a power of b, and what is that? It's just x. Okay, so it would be like this. I started out, I wanted to know what the log of 100 was. If I can work backwards, this is understood 10. So if I can represent 100 as a power of 10, well, that's just squared, right? That's exactly what we're doing. I want to represent 100 as some power of 10. What is it? That's the 2. So as long as these are equal, then it is just the exponent that I'm looking for. I've already done the work. I just need to recognize it. Okay, so that's what this thing is. Okay. Log of b to the x is equal to x, because I want to represent b to the x as some power of b. I've already got it. Exponential form, so this is the number, right? That's the number, 100. And then finally, b, this one is kind of hard to recognize, but we use it a lot as results. I've got some number. I want to represent a power of b. What is it? Well, that is the log b of x. And now this is just the x. I want to represent this number. So this is like my n, okay? Let me do it this way. I want to represent n as some power of b. That's what that does for us, okay? This gets us to the power, and now we're raising it to that power. That gets us back to that very same thing. This one is harder to recognize in general. It's just you're going to have to kind of note, here I've got these things matching, and I'm kind of working backwards. So let's use some of these basic properties, see if we can kind of pick them out. Okay, so I want to do, here's number 19, log base 19 of 19. These match. If I want to represent 19 as some power, what would it be? That's the only way that could be 1. So this is log b to the base b, that's just 1. Log 10, base is 10, that's just 1. Natural log of e, this is base e, that's got to be 1. Log to base 273 of 1, log 1 to base 273, log base 273 of 1. Anything, that's got to be 0. The only way that I can represent 1 as a power of 273, that's got to be 0. log, this is my next one, log base 30, 30 to the 10th. I've already got this represented as a power of 30. That's just the exponent. ln e to the negative 12. Very same thing. This is the base e. I've already got this represented as a base e. What's the power? That's asking what is that power to the base? That's the negative 12. And here is the one where I had b to the log b of x is equal to x. Here's an example of this. I've got 10 to the log of 14. This is taking because I want to represent 14 as a power of 10. What is that power? That is the log. That's got to be my 14. I'm just representing that as some power of b, the base 10, and what would that number be? It is just the log of 14. Eight, log 8 of 5. The very same thing. This, I wanted to represent this number as some power of 8. What was the power? It was this. So that must be that. Just the 5, not the log of that. So this one, to me, is the hardest to kind of see that this goes, but you kind of have to work it backwards, and it gets you there. I want to represent 5 as some power of 8. How do I get that power? Well, I go to my calculator, and log base 8 of that number gives it to me. Okay. Now this is not that, that's just the number. This would be, in this case, this would be, get my right calculator to do it until we do a change of base. Clear. This would be like 0.773976. Okay, so 8 to the 0.773976, that is equal to 5. But if I've got it in this, and am I asking, what is that number? That's just equal to 5, because once I do the log, 8 to that log, that's just going to be 5. Okay. So for calculation-wise, these things are on the calculator. That gives you the number. Here we just want to kind of do the graph from exponential, and I want to graph log 3 of x. So this is kind of working backwards. Okay, so this is what I want to do. I want to graph y is equal to 3 to the x. Sorry, log 3 to the x, but this is hard to do in general. Just picking out numbers, I got to go to the calculator. That's the only way I can do that. But without a calculator, what I want to do is I want to graph this, but I'm going to use the exponential form. 3, I want to represent x as some 3 to the y. I want to represent this, okay? So normally we switch y is equal to 3 to the x. So I'm going to do this. This is easier. -1, -2. We graph this, but then all I want to do is switch the numbers to do the inverse and graph this. Okay. So I'll show you both of these things and then we'll kind of work out. So let's go. I'm going to start. Here's x, and I'm actually going to graph this, and then I'm going to put this. So let me kind of do this first. I want to do this, and then I want to write the coordinate pair, coordinates, and then I'm going to switch this for the inverse. Okay. So you'll see what I'm going to do in just a minute. Okay, so I want to focus on this. This is much easier to do, but these are inverses of each other. Okay, so I'm going to go ahead and do the inverse, graph that, and then swap them to get the log. So let's do -1. So for -1, this would be 3 to the -1, which is 1/3. My coordinates is -1, 1/3. Okay. 0, 3 to the 0, that's just 1. So this is the coordinate pair 0, 1. 1. 3 to the 1 is 3. So this is 1, 3. And then I'm going to do one more, and you'll kind of get the gist of this. 2. 3 squared is 9. So this is 2, 9. For the inverse, remember all we did was when we worked on graphs for inverses is just swap these two numbers. So now I've got a point that I can graph for that. Swap these two. Swap these two. And swap those two. Okay. So on the same graph, this is how this would look. So -1, so this is kind of like -1. This would be -1/3, 0, 1, 1, 3, and then 2, 9 would be up here. So that's that familiar shape. Y is equal to x, just to give me some reference. Does it look symmetric? And now I want to graph these. At x equal to 1/3, this is now -1. Okay, so -1, 1/3 goes to 1/3, -1. This is 0, 1, 1, 0. 1, 3 goes to 3, 1. And then 2, 2, 9 goes to 9 up to 2. There and there. Okay. So mine's a very rough sketch. What I want to do is pull in Desmos and get it to do a better job for me. So let me go here. Let me bring this up. Come on. Okay. Doesn't like it when I do that from the back. Here, 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 and then it knows www. Okay, so this I want to start out with, let's say if we started out the other way. I wanted to graph out my functions. So let me see if I can find, where is my log? So here's my log, different bases. Here we were doing to the 3, so I want to go log of A. This lets me know which base, so it was to the base 3. I put that there, and then this is just x. And now it graphs out the bottom piece for me. And then I want to do y is equal to 3 to the x. And that's how the inverse, so now if I go y is equal to x, just to show this. There's that line with the symmetry around it. Okay. So any point that I get up here, I'll get the opposite. Here's my 0, 1. There's my 1, 0. If I do the negative 1, it's hard to get it right in here. Negative 133, 0.33, negative 1. So once this is here, that's the negative 1. Okay, so they're inverses of each other. This is all I have to do. So to graph a log to some base, I want to use the exponential form, do some basic grafting, and then do the coordinate pair, and then swap these to do this, because this is going to be harder to graph in general. You'd have to go to the calculator all of these points. So do the ones that you know easily, and then draw your smooth line through there. There we graph. So let me kind of do that for a different one, and we'll bring it back up in Desmos. So if I'm going to graph y is equal log 4 to the x, I would want to represent that in the exponential form that I've got, y is equal to 4 to the x, and then go through and graph that, okay? X, f of x. I want to do the coordinate pair, and then the coordinate pair of the inverse. Okay, so that would be the log. Okay, so x, let's go negative 1, that's easy. 4 to the negative 1, that's just 1/4. 0, 4 to the 0, that's just 1. 4 to the 1, there's 4. And then 4 squared is 16. This looks like negative 1 1/4, 0 1 1 4, 2 16. Because it's 4 squared, 4 times 4 16. Make sure I got this right. And then I just swap these things. 1/4, negative 1. 1 0. 4 1, and then 16 2. And then I can graph these as a pair. Okay. Go to our functions. This was under our miscellaneous functions. Here was our log to base A. That's what we originally wanted to do. Here's our 4. Here's our x. And then our corresponding y is equal to 4 to the x. So here I would graph these points and recognize the exponential, just increasing, flip them, and then go ahead and do the inverse, which is the log 4. That gave me some points that I could draw and then get through there. Okay. That's how I graph logs. Okay. Now, log by themselves, once we have a basic function, then we can do the very same transformations. Okay. So if I know, and I can do this one, this is a B, looks like a 10, but it's a base, any base B. If I graph y is equal to b to the x, do the inverse, okay? If I graph those, so I know what this looks like, I start here, graph this, do the inverse. If I know what this is and I can get to it that way, then f, so if I start out log b to the x minus h units right. I start with this and I move it to the right. Okay. And then if I go log b, x minus h plus k, this one's easy, k units up. But if I do this, I need to do the scaling. Once I'm doing that, I need to kind of follow the order. I take log b, I know what this looks like, shift it to the right h units. I do the scale, so anytime the x is staying the same, once I've shifted over h, but the y value from this, I'm multiplying times a. So I'm scaling it up if it's greater, right? And then I take all of that and just shift it up. So all of that gives me the transformations needed to do that. Okay, so I can do these by hand by doing this, doing some simple multiplications of whatever a, and then once I get that number for the new y, then I can just shift that up to the x. All of these start here, shift over, what is my corresponding y value, multiply it times a, scale it, and then shift the whole graph up. So it may take you a couple of intermediate graph points to get you up there, but you can start and do all of this by hand. So this is for b greater than 1. I've kind of focused on this. The domain, negative infinity to infinity, that's, this is this piece of it. Okay. The range is 0 to infinity for the base function, the exponential. Goes to 0 and infinity. Okay. The horizontal asymptote, y is equal to 0 out to this end. It's only a one-ended horizontal asymptote. And when I switch, okay, this is for any y is equal to b to the x, 0, 1, x is 0, whatever this is a 1, it passes through there. This, if you're considering b greater than 1, this is kind of growing. And then if I do this, this is what I want to do. I shift, or I take the range, make it the domain. The domain goes the range of the inverse. This is always true. Domain is the range is the domain of my inverse, okay? Instead of the y equal to 0, I have a vertical asymptote x equal to 0. Okay, and then that passes through 1, 0. I'm just switching that number, okay? The vertical asymptote, if I go back here, this horizontal asymptote goes to a vertical asymptote. Okay, so what does that really tell us? Okay, so if I have some log of x to base 3, let's say base 3, this number has to be greater than 0. If I go back to this graph, here this was greater than 0. If I go back here, this is only for x greater than 0. So whatever I'm looking at, This is going to be like the square root. We're going to treat this just like the square root. You remember if I wanted to do the domain of like f of that, I said this has to be greater than or equal to 0. Now this has to be strictly greater than 0. So the domain of this has to be greater than 0, plus 4, x had to be bigger than 4. Okay? And it doesn't matter. Doesn't matter this. This is what matters. So the domain would be 4 infinity, not equal to 4. Here I could have this being equal to 4, the square root of 4, square root of 0 is 0. This, I can't do this because I want to know, okay, so if I'm saying what is log 4 of 0, I want to represent 0 as some power of 4. There is nothing I can do except make this smaller and smaller to a negative number, okay? So the y value, as I start going back to here, as I start getting closer and closer to 0, this is a negative number, but I can't make it just 1 over, but this goes to negative infinity. Gets closer and closer, it's not equal, but this goes to 0. Okay. That's what you're saying in equivalent form. Okay. So it's the log base 3 of x shifted right by 4 and then up by 1, but that's the domain, okay? Shifted left by 3, log 2 to the x shifted left by 3. Here's log 2 to the x, but then I reflect negative, so 2 is greater than 1, so it should have been like that. Now we reflect, or it should have been like that, and then we reflected, here's the bottom. Where it was negative, it's positive, where it's positive, it's negative. And that would be the 0, 1. Okay, here's this we would have to look at. You got to break this thing down. You're looking at 2 pieces. This is log to the base 10. This is x minus 4x plus 1. 2 factors, difference being 3. This is the same thing here. The reason I did this is that both this has to be greater than 0. Okay, so this is negative, negative, or positive, positive. So here I've got set each one of these equal to 0. There's 0. Here's 4. Okay, so this is a parabola. Opens up. This has to be the negative, and that has to be the positive. These are the zeros. Can't be negative, so the domain goes negative infinity, negative 1, union 4 to infinity, both of those pieces. And then this is the graph of what that would look like here. So for this and this domain, I'm graphing it down and then the up. I'm just picking out numbers here and kind of working backwards to get this. And that's what that would look like. Okay, so we'll look at some applications during lab. I'm going to hold off on the recording there.